Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. So in the previous lecture what we have seen thus far is that given any matrix A, as long as its eigenvalues are real, whether they are repeated or not, whether the matrix itself is diagonalizable or not, at best we can go for this Jordan block form, and once we get to the Jordan block form, evaluating the exponential of the Jordan block form, though not as easy as evaluating the exponential of the diagonal form, is nonetheless much simpler than evaluating the matrix exponential for any arbitrary matrix, yeah, without any particular structure, right. And since we know that any matrix can at least be converted into its block Jordan form, therefore we have an easy recipe to get to the matrix exponential of a matrix, right, for a given matrix. So that is what we have seen so far. However, as I said in the previous lecture also, we have so far tiptoed our way around this problem of matrices which have complex eigenvalues. So I will not give you a very general method rigorously, but at least I will again take a numerical example which will probably highlight to you the general method for dealing with such matrices, okay. And I will summarize at the end without any proof, but you should be able to put in the pieces together and combine and come up with a kind of a rough proof for the claim that any matrix, irrespective of whether it has a block Jordan form or a diagonal form or a pair of complex conjugate eigenvalues or a combination of all three of them in different ways, I will always have an easy way, quote unquote an easy way of obtaining the matrix exponential for that given matrix, provided I can partition them in a sort of a block diagonal form, right. And hopefully through this example today, which is going to be, I promise, the last example for obtaining matrix exponentials that we shall see, yeah, you will hopefully see the culmination of this procedure, right. So let me take this A matrix, yeah, I will not take the B and C and the D matrices because those we are only concerned with when we are obtaining the complete solution. Right now I am just interested in obtaining the matrix exponential, and I have shown you once you can obtain the matrix exponential, obtaining the overall solution is not really a big deal, just requires a little bit of integration, that is it, because in both the 0 input and the 0 state part of the responses, it is this matrix exponential that holds the key. So let us take this 2 by 2 case, this matrix minus 5 minus 2, and once again because I have already done the calculation earlier, so I know that this determinant of lambda I minus a is equal to 0 implies the lambda is equal to minus 1 plus minus j2, yeah. So this is exactly the case that we have not discussed yet. So we wonder if there is an easy way, just like the Jordan form for real eigenvalues. Of course you can do the Jordan form for complex eigenvalues as well, but then you will have complex eigenvectors, which is something we are keen to avoid. So we wonder if there is a somewhat easy way, a recipe to obtain a matrix exponential for this matrix A, right. So let us go about this business now. So now notice that if you try to find out this A V is equal to lambda V, yeah, then you have to have A times V is equal to minus 1 plus j2 times V. Now note, if you choose V to be a purely real vector in Rn, then this will have no solution other than the trivial solution, right. Why? Because on the left hand side this A matrix comes from an n cross n entries of all real numbers. So the left hand side is completely a matrix of a vector that is an n tuple of real numbers. On the right hand side, on the other hand, this comes from real entries, then this will also come from complex entries. So you cannot have, and this is definitely going to be complex with a non-trivial imaginary part, yeah. So this cannot be equal. So then you must have this V coming from a complex n tuple, yeah. In other words, let me write that down. So let me call that U then, or rather, yeah, let me call that U. Let me call this U, because I am then going to split up this U as V and W, okay. Yeah, so this is U. So then let me say U is equal to V plus JW, and now you can see that this W comes from an n tuple of real numbers, V also comes from an n tuple of real numbers, and this is a complex vector. That is all that you need, right. In order to cook up a complex n tuple, you need a real n tuple plus J times another real n tuple, that is it, right. So therefore, now if you want to solve for the eigenvector of this, you will have to write the equation as A plus JW, A times V plus JW is equal to minus 1 plus J2 times V plus JW, right. The funny thing is, now if you try to write down the eigenvector eigenvalue equation for the conjugate of this, you will really not end up with something new, because see, if you take the complex conjugate on both sides here, you will get V minus JW is equal to minus 1 minus J2 times V minus JW. This is all about the fact that if you take two complex numbers Z1 and Z2, their overall conjugate, that is going to be nothing but the conjugate of Z1 times the conjugate of Z2. That is all the result that I am using here, yeah. So entry wise, this is a real matrix, so A conjugate is just A itself, yeah, and V plus JW, where V and W are n tuples of real numbers, their conjugate will be V minus JW, yeah. This is just the change of sign here, and this is also that same thing happening here. So basically these are the two eigenvector eigenvalue equations for the complex conjugate pair of eigenvalues, right. Now you see that there are two unknown vectors and there are two equations, so by rights we should be able to solve for them. In fact, I do not need both equations, I can actually just focus on this first equation, and separately, because the real and the complex parts are, as in any complex numbers property, if two complex numbers are equal, then different independent of one another, the real parts must be equal and the imaginary parts must be equal. So I can just focus on this equation and forget about this, and I will get, from equating the real parts and the imaginary parts on both sides, I will get my equations. So what is my equation going to be going to look like? Well, I will just have this A times V plus JW is equal to minus 1 plus J2 times V plus JW. So I will have AV, which is the real part on the left hand side, equaling minus V minus 2W, this J2 times JW, so J squared is minus 1, so minus 2W, and then the imaginary part on the left hand side, AW, remember these are not numbers but these are n tuples now, yeah, A times V is another n tuple, A times W is also another n tuple. If W is an n tuple, AW is an n tuple, if V is an n tuple, AV is an n tuple. In this case it is just a 2 tuple, it is a 2 by 2, that is the reason why it is 2 tuple. In general it could be any n cross n. Okay, what about AW? So on the right hand side, what is the imaginary part? You see 2j times V and minus 1j times W. So it is going to be minus W plus 2V, right. That is all there is to it. Now much in the same fashion, if I now write, so AV is a column, n tuple, column of n tuples, AW is a column of n tuples, so I can cook up a matrix, yeah. So this is going to be of size n, this is going to be of size 2. So an n cross 2 matrix. On the right hand side, I will have essentially, if I write this as V and W, then what sort of a combination of V and W is this? Yeah, I would require, so this is of course n and this is 2, so I would require a sort of 2 cross 2 matrix here, right. So what is this first column equal to this first column is equal to minus 1 times V minus 2 times W, yeah. So then it is minus 1 times V, yeah, and minus 2 times W. What about the second column AW, that is equal to minus 1 times W, so it is minus 1 times W, yeah, the second column here, note, is minus 1 times W and 2 times V, so this is going to be 2. Now notice something interesting here, then in the next step I can just write this as A VW is equal to VW minus 1 2 minus 2 minus 1, an interesting form. This is actually a skew symmetric matrix, not really a skew symmetric matrix, part skew symmetric. Okay, let us forget about it, it is not really skew symmetric because the diagonal entries are not 0, yeah. So it is basically a diagonal matrix plus a skew symmetric matrix, but anyway forget about the name. Skew symmetric means Aij is equal to minus Aji, yeah. So instead of Aji being equal to Aij like in a symmetric matrix, a skew symmetric, the sign is just the reverse. So obviously then by definition the diagonals must be 0, but this is some lambda times I plus a skew symmetric matrix. Anyway, we will not bother with that. The crux of the matter is, you see this is very similar to something we had done earlier. Suppose, now suppose this, in this case n is equal to 2, yeah. Now suppose VW is equal to T is invertible, suppose, okay, we will later show that it is indeed invertible in this case for the 2 by 2 case, and in the general case when you augment it with sufficient number of other eigenvectors, yeah, we will see that it is invertible, but in this case at least suppose this is invertible, then what can we do? This is T, this is T, right. So now in that case can we not write T inverse AT is equal to minus 1 2 minus 2 minus 1, right. If we do that, then we would have actually obtained, I put it to you that we would have obtained a simpler form for e to the at, yeah, in order to get from this e to the at, original e to the at, this is actually a simplified form, although this is not diagonal, neither does it appear like the conventional Jordan form for real eigenvalues, but I am claiming that this is going to be a simpler form. So of course there is a catch, if T is invertible. Now what is the guarantee that T is invertible? I have not even given you any such guarantees, right. So for the moment just take a leap of faith with me and we will revisit this whether it is invertible or not. Assume that it is invertible, yeah, then is it true at all that this matrix this of this form minus 1 2 minus 2 minus 1, this is indeed of a simpler nature? Indeed, what are the entries at the diagonal and the off diagonal? Now notice from this particular example I am not going into the general case. Suppose A belonging to R 2 cross 2 has eigenvalues alpha plus j beta with eigenvectors again v plus eigenvalues alpha plus minus j beta, yeah, v plus minus jw, then, and this is going to be the claim, there exists T such that T inverse AT is equal to alpha alpha, and notice what the form here is, alpha alpha beta minus beta, yeah, and now is equal to let us say some delta, yeah, not the lambda matrix because the lambda we have reserved for the diagonal matrix, yeah, so this delta. Now I am claiming e to the delta t is not difficult to evaluate. In fact, it is easier to evaluate than the original matrix, that is this. Why? Because this has a repetitive pattern. Okay. So now what is the pattern? E to the delta t is going to be I plus delta t plus delta square t squared by factorial 2 plus dot dot dot. So the key again is to observe whether there is any pattern in delta to the power k by factorial k. Yeah, what is the pattern in this? So notice that well, delta in its rudimentary form is nothing but the real part of the lambda, the imaginary part of the lambda, then the negative of the imaginary part of the lambda, and again the real part of lambda. This is what delta in its rudimentary form is. What about delta squared? Well, let us say alpha beta minus beta alpha times alpha beta minus beta alpha. So I will get alpha squared minus beta squared, yeah, then twice alpha beta, then minus twice alpha beta, and again alpha squared minus beta squared, like so, right. Now once we have gotten this far, what do we observe? Well, you see that if you take alpha plus j beta whole squared, yeah, observe what is this? This is alpha squared minus beta squared plus 2j alpha beta, right. So if that is the case, then this is going to be nothing but, this part is going to be real part of lambda squared, and this 2 alpha beta, forget about the j, this is going to be the imaginary part of, so let me remove that equal to sign, this is going to be the imaginary part of lambda squared, where lambda is equal to alpha plus j beta, remember, yeah. So clearly then this holds when you raise to the power 1. Now suppose, so we are going to apply mathematical induction. So suppose lambda to the power r is equal to real part of lambda raised to the power r, imaginary part of lambda raised to the power r, minus of imaginary part of lambda raised to the power r, and real part of lambda raised to the power r, like this, okay. Then what is lambda to the power r plus 1? Lambda to the power r plus 1 then turns out to be nothing but, again I put alpha beta minus beta alpha, and then this real part I call this r to the power r. So this is basically yeah, this is r to the power r, sorry about that, this is r to the power r, this is I to the power r, this is minus I to the power r, and this is just a symbol I am using, this is just a shorthand symbol for this. You raise lambda, remember this is not the real part of lambda raised to the power r, okay. First you raise lambda to the power r and then you take its real part, like we did here. First we raised lambda to the power 2 and then we took its real part. We did not take like the real part of lambda isolated and took its square, then it would be just alpha squared, right. So there is that difference, and this is r to the power r. So if you now apply this, you will see there is alpha r to the power r plus beta r to the power r, yeah, sorry, plus beta minus beta I to the power r, minus beta I to the power r, what was I thinking, I to the power r, and this is alpha I to the power r plus beta r to the power r, again this is minus beta r to the power r plus minus alpha I to the power r, until finally minus beta I to the power r plus alpha r to the power r, yeah. Now what is the guarantee that this is indeed going to be like, so what we need to show is that if you just focus on this part, we need to show that this is equal to what? It is going to be equal to the real part of lambda to the power r plus 1, and that this part is going to be equal to the imaginary part of lambda r plus 1, lambda to the power r plus 1. Okay. How do we show that? So, you just say that alpha plus j beta to the power r plus 1. Yeah, now you can apply this de Moivre's theorem, right. So, you know that this is basically, you can represent this as a sine and cosine. Yeah. So, maybe you can just look that up. So, this is going to be nothing but alpha squared plus beta squared to the power r plus 1 by 2 times cos r plus 1 theta plus j sine r plus 1 theta. Yeah, where cos theta is equal to alpha by square root alpha squared plus beta squared, and sine theta is equal to beta by square root alpha squared plus beta squared. So, we need to show that this times this is equal to this, which is in turn equal to this, yeah, and this is equal to the sine times, so sine of r plus 1 times this into this. Yeah. So, I leave that to you as an exercise. It is really an exercise in mathematical induction. I shall really not be drawn into this, but I have provided you enough hints and enough like steps along the way. You can complete this proof, but otherwise you can just carry on with me with the faith that this is indeed so, and that any arbitrary term you pick up here, this is of the form, this delta to the power k, when delta is represented in this form, this is indeed convenient for exponentiation in the matrix sense, because this is going to be nothing but 1 by factorial k times the real part of lambda to the power k. This is 1 by factorial k times the imaginary part of lambda to the power k. This is again 1 by factorial k with a minus sign, the imaginary part of lambda to the power k, and this is 1 by factorial k times the real part of lambda to the power k. Okay. Now, if you keep summing this, yeah, so you notice that this is going to be nothing but summation k going from 0 to infinity, yeah, delta to the power k by factorial k. So, you sum together these terms. Now, entry wise if you look, what is this? What is this after all? Yeah, this is nothing but, you see, the real part of lambda to the power k, you sum over this. Yeah. So, if you sum over this real part of 1, can you not take the sum inside? Yeah. So, for example, you take two numbers, if you take z1 and z2 and take the real part of that sum, that is equal to nothing but the real part of z1 plus the real part of z2, right. So, applying the same principle here as well, where did I put that? Yeah, here as well. Now, if you put a summation next to both sides, this infinite sum from 0 to infinity, then I can write this as simply the real part of summation lambda to the power k by factorial k, the imaginary part of summation lambda to the power k by factorial k likewise, yeah, and the remaining two entries you know what it is the minus of this and it is just the plus of this, yeah. So, that is my matrix. Now, what are these individual terms? Yeah. So, if you take, now look at e to the lambda t, lambda is going to be equal to, yeah, e to the alpha plus j beta t, yeah. So, that is going to be e to the alpha t times cos beta t plus j sin beta t. So, this is going to be just the real part, right. We are going to pull out the real part and the imaginary part of these fellows, we are going to rip them out. So, what is the real part of this? Yeah. So if you take the real part of this, apply the real part operation here, yeah. So if you just apply to the real part of this, what is this? It's going to spit out e to the alpha t cos beta t, and if you apply similarly the imaginary operation on this, you are going to get e to the alpha t sin beta t. So then e to the delta t turns out to be nothing but this e to the alpha t pulled out outside, and look, inside you have just this cos beta t sin beta t, which is a pure rotation matrix. If you have come across this in some other course, you would know, yeah, cos beta t. This is all there is to it, yeah. So once you have gotten it to this form, although this is neither the conventional Jordan form that you have learned for real eigenvalues nor the diagonal form, yet we have shown you that even this is easy to implement. So by the same token now, if I have been given this particular matrix, in my case this -1 plus j2, I can now blindly, once I have transformed it here, let me go to the specific numerical example at hand. Yeah, this was the example that I had taken, -1 plus minus j2, yeah. If I take -1 plus minus j2 now, I can directly in fact blindly write this e to the delta t, where delta is, remember, -1, 2, -2 if I am not mistaken, right, yeah. So then this is going to be equal to e to the minus t cos 2t sin cos 2t sin 2t minus sin 2t. So that is going to be my e to the delta t straight away, right. So not very difficult. So this was the problem that we wanted to solve, and we found a way around. Of course the one catch is, now you might ask whether at all this fellow is diagonal, I mean this T matrix that I had chosen and I had not proved whether this T is going to be invertible, in other words whether V and W are linearly independent. Now suppose it is not, suppose V and W are not linearly independent, then what happens? Then V is equal to some gamma times W, yeah, because they are real vectors, so this gamma must also be a real number. So V must be some real number times W, that is the only way they can be linearly dependent. If that is so, then now look at the original equation. What did we have there? We had V plus JW is equal to this lambda, which in our case was -1 plus j2. So lambda was -1 plus j2 in our example, plus minus j2, whatever, lambda times V plus jw. So then what would we have? We would have A times this V is nothing but this gamma times W, no. So I can substitute it here. So let me put this gamma times W plus jw is equal to lambda and then gamma W plus jw, yeah. So this gamma is obviously some non-zero number, yeah, because we were searching, because this V and W are both non-trivial vectors, no. So gamma has to be non-zero. So in that case I just say that this is gamma plus j taken out common on both sides, and then I have A times W is equal to lambda times again some gamma plus j pulled out, then W. So now this gamma plus j is definitely not equal to 0, so I can cancel it out on both sides. So then I will end up with the same contradictory situation that I wanted to avoid. Yeah, look, this lambda is complex number, W is a real n-tuple, A is a real matrix. So on the left hand side I must have a real n-tuple, on the right hand side this W is a real n-tuple, but this lambda is spoiling the party because it is now a complex number. So on the right hand side I have a complex n-tuple, on the left hand side I will have a real n-tuple. So therefore my initial premise that this V and W are linearly dependent cannot be true, right. So V and W are definitely linearly independent, in which case I shall always be able to invert this matrix T and thereby obtain a delta of this form, and once I have obtained a delta of this form I can always take the e to the delta t in a very convenient manner like I have shown here. So to summarize all the cases, and this is going to be the crux, the climax of everything, whether you have real eigenvalues lambda 1, lambda 2 till lambda k, so these are all real, yeah, and then you have lambda k plus 1, lambda k plus 1 some r times repeated, yeah, lambda k plus 2 some k plus 2 some r1 times repeated and so on like this, and finally you have lambda k plus I do not know r1 r2, yeah. So there are k eigenvalues that are real and distinct, then there are r1 repetitions of one eigenvalue, r1 real repeated, yeah, r2 real repeated, likewise you can have r3 and all, but I am just taking two such clusters of real repeated, and then lambda k plus 3 and lambda k plus 3 conjugate, lambda k plus 4 and lambda k plus 4 conjugate, say for instance. So these are complex eigenvalues, complex conjugates, yeah. So then what sort of a block matrix do you expect in this case? Well, I am saying that there will always exist, for these fellows you can find k eigenvectors, yeah. For these fellows you may not find r1 plus r2 distinct eigenvector, I mean linearly independent eigenvectors, but you will at least be able to find Jordan chains, yeah, Jordan blocks, yeah. So let me write that down. First you will find lambda 1, lambda 2 like this till lambda k. So these are all simple eigenvalues, you will get this block, the rest are all zeros, a big 0 here. Then for k, this lambda k plus 1, which is going to be an r cross r size, you will have you can have multiple chains within this r1 cross r1, right, yeah. So you can have, let us say lambda k plus 1 1 0, lambda k plus 1 1, yeah, 0 0, lambda k plus 1, and then you can have maybe some distinct lambda k plus 1 like this. So you can have multiple chains, multiple Jordan chains within this single Jordan block of r1 size, yeah. So here also you can have these zeros like this, okay. Then you have another Jordan chain of r2 like so. So this is r2, and let us say you have lambda k2 1 0, lambda k2, and then lambda k2 like this, so on. And finally you will have these complex conjugate pairs, but if you want them to be entered in real terms, then you will have to have real I minus I r, yeah. And then finally for the last one, that is k plus 1th, you will have r1 I1 minus I1 and r1, okay. So this is typically the form in which you expect. And now if you want to take the, so this is going to be your transform matrix, so T inverse AT, there will always exist a T that will allow you to take your matrix to this form, okay. And once you have got into this form, the job of getting the e to the AT, so let us call this matrix as, what should I call it, maybe the j tilde is equal to this. So then if I want to get e to the j tilde t, all I need to do is individual blocks I can take their exponential. So I will have e to the lambda 1 t dot 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 till e to the lambda k t, that will take care of this block, yeah, this block will be sitting here like this. Then the next block, I know how this Jordan block looks, right, I will have e to the lambda k plus 1 t, e to the lambda k plus 1 t, and in the off diagonal, the upper triangular structure, I will have the polynomial times those. So t times e to the lambda k1 t, then t square by factorial 2 times e to the lambda k plus 1 t likewise, and the lower block will be 0. Similar thing with k plus 2 eigenvalue, this also will have an upper triangular form like this, yeah, the lower triangular part will be 0 below the diagonal, the sub diagonals will be 0, and now this one will have this e to the alpha t times this cos sine, the rotation matrix, and the last one will have e to the some alpha bar t, and again cos sine like this, yeah. So just by taking this similarity transformation suitably, I find that the job of obtaining this matrix exponential becomes considerably simplified, which is what our original goal of this entire task was, okay. Of course, to make matters even more complicated, you say that even these complex poles, can be repeated and may not be perfectly block diagonalizable, yeah, in which case they might also have to be written in the Jordan form. So for example, you happen to have real rotten luck and you run into a system which has alpha plus j beta, yeah, and another again pair of eigenvalues which is also alpha plus j beta, right, but you have only one eigenvector v plus jw. So then this is not block diagonalizable, so then you will have like a block Jordan form, so you might have an identity here sitting then, okay, but those are like very corner cases, we will not get into the detailed discussions, but you can see how this will change then, yeah. So in such a case you will have this sort of a situation arising, okay. So then how to take their matrix exponentials? Well, they will look similar, I will just say that they will look similar to this Jordan block here, the real Jordan block, in the sense that these will contain polynomial times cosine or sine times e to the alpha t, okay. So in the real case the cosine and the trigonometric terms did not make an appearance, but in the complex case the trigonometric terms will appear. So the take home message from all this is e to the at, now that you want to get this, it will be basically t e to the delta t times t inverse, yeah, can only contain terms of the following form, and this is going to be very crucial when in a few lectures from now we discuss this idea of stability in the state space form. So what are the following forms? Terms like e to the lambda t, where lambda is a real number, terms like t to the power k, yeah, upon, okay, well, let us not put upon factorial because it will be linearly combined, some alpha times t to the power k e to the lambda t, where alpha and lambda are real numbers and k is a positive integer, yeah. So that is one type of term, that is a second type of term, and a third type of term either beta t to the power k, so this could be positive integers or non-negative integers, so this positive integers union, it could also be 0, yeah, that could be the possible k. The third type of term is beta t to the power k cos, e to the gamma t cos delta t, or beta t to the power k e to the gamma t sin delta t, where delta, beta, gamma are real numbers and as before k is some non-negative integer, yeah. So these are all the type of terms that can enter. So every entry of e to the at is of these forms or their linear combination, or their linear combination. So either you add them or multiply each of these entries by some scalar and that is all you will get. So e to the power at can contain no term other than any term of this form, okay. Please remember this is going to be of fundamental importance when we want to prove to you what the condition for stability of a linear time invariant system is, yeah. It turns out it will be intricately linked, in fact it is totally defined by the eigenvalues of this matrix A, and if you put your thoughts behind this you will already be able to guess what that condition for stability will have to be like, okay, but there are still some fine points there, we will discuss that later as and when we get there, okay. So with that we really draw a line beneath this obtaining this matrix exponential. We have discussed almost as exhaustively as an undergraduate course would permit us to, how to obtain this e to the power at matrix for all different kinds of eigenvalues, yeah, and for all different kinds of scenarios you might encounter, complex eigenvalues, real repeated eigenvalues which are not diagonalizable, yeah, all those cases we have seen and we have found a way around each of those cases, yeah. So provided you can cook up sufficient number of vectors, either eigenvectors or generalized eigenvectors, yeah, and in case of complex eigenvalues, eigenvectors which have both a real part and an imaginary part, just put the real part of the eigenvector aside and the imaginary part of the eigenvector aside, yeah, and then put them side by side, stack them up. So as long as you have been able to stack up n such linearly independent eigenvectors, yeah, or generalized eigenvectors, you will always have at least a generalized Jordan form in the real, in terms of real entries. Yeah, and as long as you can do that, as I have shown you here, it takes a bit of an imagination or a bit of work maybe, but you should be able to show that this is all there is to it by visual inspection. Yeah, this is all that your e to the jt or j tilde t can look like. Of course, this j tilde I have here named it delta. Maybe I should call it j tilde here, yeah, to be consistent. Yeah, so this is the j tilde. Right. So that is all we wanted to discuss, and now in whatever time is remaining in this lecture and probably a part of the next lecture, we shall be focusing on a brief journey into linear time varying systems. Right at the beginning we said that in this course we shall only concern ourselves with linear time invariant systems, yeah, and that is when we introduced Laplace transforms and said that this provides us with a very beautiful handle. But now state space methods are not really limited to linear time invariant systems. In fact, we can also go for nonlinear systems and model them in their state space form. We will not do that in this course, but at least the linear time varying case we can give you some brief idea. So here is how the representation will look. Remember, this is not going to be a constant coefficient differential equation, yeah, the coefficients could be functions of time themselves, in which case this A matrix, the entries of the A matrix will happen to be functions of time as well, yeah. So remember the A, B, C, D matrices, they will all tend to be, their entries will all tend to be functions of time, alright. So that is all the way there is to describe this, but remember that now if you define this as your initial condition, yeah, life is no longer simple, in the sense that in a time invariant system, if you applied an input, or if you know the initial condition at this t0 instant, and if you look at the response at the instant t0 plus tau, it would be the same as if you applied the input at the 0th instant and you looked at the response at the tauth instant, yeah. This and this would be one and the same. So this is for LTI, yeah. But now in a linear time varying system, you have to be careful, that is what makes this so complicated, because now if you apply an input at the time t is equal to 0, yeah, and you observe the output at tau, it could be like this. On the other hand, if you had to apply the same input, or maybe the the initial condition to be the same at say t naught, and if you want to look at the response at t naught plus tau, yeah, so you might find, in fact in most cases you would find, that these two are not equal, right. Then what do you do? This method of finding the state space equation solution and all this does not work here. So here what we start with is that suppose we know that f1t, f2t dot dot dot, these are all functions of time, and these are all n tuples, by the way, these are all n tuples till fnt, yeah, are all solutions of x dot t is equal to, so first we will look at the homogeneous case, okay, with the initial value and no forcing function, no external input, okay, for different initial conditions at t is equal to t0, okay. Not just that, suppose further that f1t dot dot dot, so remember these are n tuples of functions, okay. So each of these f1, f2, f3, these are an n tuple, okay, through till fnt are linearly independent. So important thing here to notice, I am supposing this, that suppose we know this. In general this is not a trivial supposition, okay. I am supposing it here to push through towards a way of handling this, but in general in a linear time varying system this is why it is so challenging, because these suppositions, the ability to find n such linearly independent n tuple of functions which are indeed the solutions of this system, this linear time varying system, yeah, that is itself not a trivial task, it is very difficult, okay. So there is no one foolproof method that will allow you to do this, in general it is a very challenging problem, okay. Just because we can represent it in a state space form does not mean that the solution of this is as easy as that of a linear time invariant system, which is why this is not classically a part of your syllabus in undergraduate control theory, right. But anyway, we will see that even with this we will see that we have a bit of a unifying theory here and some understanding, some insights into this. Suppose further that these are linearly independent. What does linearly independent mean? Linearly independent means that is if C1 F1 plus C2 F2, of course these are all functions of time, plus dot 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 plus Cn Fn is equal to, sorry, Cn Ft is equal to Fnt is equal to 0 for all t, then C1 C2 dot 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 till Cn are all equal to 0. The same notion of linear independence. So the important thing here is, now suppose you take the function e to the t and e to the 2t. So the question is, are these linearly independent? So you take for instance say, what should I say, e to the 2, this is a real number, e to the 2 times e to the t, yeah, or rather should I take, okay, minus e to the 1 times e to the 2t, yeah. What do I get? So at t is equal to 1 second, this is equal to 0, no, yeah. But does that mean that these two are linearly dependent? Well, of course not. The point is, at this one particular value of time you have found this defect, yeah. So if you plug in t is equal to 1, then this is e to the 2 times e to the 1, which is e to the 3, e raised to the power 3, and this is also e raised to the power 3, so they are equal to 0, where of course this is my C1 and this is my C2, and you might be jumping up and down saying, well look, I have found a pair of a set of C1 and C2, no, so this not this minus, this entire thing here, so I can say that this plus of minus E1, yeah. So you might say this minus e to the power 1 is C2 and plus e to the power 2 is C1, and therefore I found a couple of non-zero real values such that at a particular time instant they vanish, their linear combination vanishes, so therefore it is linearly dependent. No, it has to be true for every t, remember. So this part is very crucial, yeah, it has to be true for all t, and now the moment you choose some other value of t, obviously it is not true. So you can try checking that for all values of t, if you want something to be true, like if you want C1 e to the t plus C2 e to the 2t is equal to 0, yeah, for all t, then that will only imply that C1 has to be equal to 0 and C2 has to be equal to 0, yeah. You can try proving this. So therefore these are linearly independent, but it turns out that in case of this linear time varying system, there is something beautiful that is going on here, okay. So we will assume something here, we will assume, and this we will not prove because this is well beyond the scope of any course, this will actually be a part of some graduate level course on ordinary differential equations. We will say that so this is a very critical assumption, this is actually provable, but we will not prove this here. So for the time being you can take this as an assumption, but this is actually a fact, yeah. There is something called a Bellman-Gronwall lemma which allows you to prove this. The solution of a linear differential equation for a given initial value, given set of initial values rather, set of initial values is unique, okay. So we will not prove this, obviously this is well beyond the scope of this course, but the solution, first of all the solution exists, yeah, there is something Lipschitz condition, okay, again very advanced topics, we will not cover this here, and also by Bellman-Gronwall lemma you can show that the solution is going to be unique for such linear differential equations. So after all, this state space representation is coming from some ordinary differential equation with non-constant coefficients, where the coefficients themselves are functions of time, yeah. So essentially this is again like in the time invariant case, this is the representation of an nth degree differential equation as n first degree differential equations, okay. So essentially there is no other difference between this and the linear time invariant system, other than the fact that the coefficients here are allowed to be functions of time rather than just constants here, okay. So this is what we shall assume, that this we will not prove, we will take this to be true, to be given to us as true, okay. And now given that this is true, yeah, given that we have convinced ourselves that this is true, here is what we next go on to say, right. So this is really where the crux of the entire matter is. Now claim, suppose Ft, this is a matrix, remember, n cross n defined by F1t, F2t dot 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 Fnt, where Fit is a solution of x dot is equal to Atxt for some initial condition x1 of 0, yeah, this superscript 1 0, okay, that is a full stop. So suppose this is true, then if f of t is non singular for some t, it must be non singular, oh sorry, rather it must, if it is singular, I am sorry, please excuse me, if it is singular for some t, then it must be singular for all t. So what I am saying is, just to give you a brief understanding of this, in this case we saw that even though for a particular value of time t is equal to 1 second, yeah, we got a non-trivial combination of C1 and C2 such that C1 times e to the t plus C2 times e to the 2t is equal to 0, we would still not say that e to the t and e to the 2t are linearly dependent, because that only happens at some particular values of t but not at every value of t. But it turns out that in this case, what does it mean that to say that Ft is singular? When we say that Ft is singular, Ft is singular, it just means F inverse of t does not exist. It also means both ways determinant of Ft is equal to 0, and it also means that there exists C an n tuple of numbers such that C is not equal to 0, identically the 0 vector, and f of t times C is equal to 0, yeah, because then that means that the linear combination of the columns of f, yeah, this just means that the linear combination of the columns of f turns out to be 0, and it is a non-trivial combination of the columns, therefore f cannot be a full rank, therefore f is singular, yeah, and f is singular means it cannot be inverted, it means that its determinant vanishes, yeah, all these are equivalent conditions, yeah. I hope that you brush up a bit on some preliminary linear algebra you might have done in your undergraduate courses, and then you would see that this is indeed the case, alright. Okay, so now having seen this much, what can I further say about this, yeah. So if Ft times this C is equal to 0, now I have to show that unlike in the usual case where there is no ODE and nothing, I am just talking about two functions. So if I am asked to check whether two functions are linearly independent, then I have to basically find whether there exists some non-trivial set of gains such that I take the linear combinations of those functions by multiplying them with those gains, and whether it can turn out to be 0 at all or not for all values of the argument of the function, not just for any defective value of the argument. Okay. But here I see that if it fails to be non-singular for one value of t, it will be identically non-singular, I mean it will be identically singular for all values of t. And why is that? Why should that be the case? Yeah. So that is what we need to then establish, and it turns out that one property we shall be using to prove this is basically this uniqueness of the solution. How so? So notice, suppose there exists T1 such that f at T1 is singular. So this is the proof of the claim. Okay. Suppose there exists some T1 such that f of T1 is singular. Then what happens? Then we say that there exists C, an n tuple of vectors such that C is not equal to 0, but f of T1 times C is equal to 0. Alright. But remember, what are the columns of f of T1? Columns of f of T1 are basically n solutions, n different solutions, yeah, n different solutions of the system of equations, that is x dot is equal to Ax, this equation, right. The columns of this matrix F that I have now cooked up, this defined here, these are basically solutions. Okay. So now if that is so, then suppose I have a system which I start observing from the instant t is equal to t1. So then my initial condition is what? Yeah, my initial conditions could be, then my possible initial conditions could be C1 times f of f1 of t1 plus C2 times C2 times f2 of t2 plus dot 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 till Cn times fn of t1, sorry not t2, t1, yeah, where C is equal to C1, C2 dot 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 till Cn. In other words, what I am saying is that this is equal to my initial condition. So this is going to be my x1 0, x2 0 dot 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 till xn 0. Okay. So I am saying that my observation time starts at t is equal to t1, but at t is equal to t1, if I choose this as my initial condition, so this is by my choice. Now of course you check that this can be an initial condition, no? There is no reason why this can't be an initial condition, right? Nothing prevents me from putting an initial condition like this. But what is this initial condition? This is going to be nothing but all zeros, no? By my very definition, this is because since ft times f of t1 times c is equal to 0, because I have chosen that at some instant of time this f of t1 is singular. So if that is so, then this is 0. So remember, if this is an ODE, yeah, and its initial condition is 0, then what is a trivial solution for this system of differential equation? So then one solution of x dot t is equal to at xt with x 0 is equal to 0 0 0 0 is xt is identically equal to 0, yeah. So if it is identically equal to 0, then obviously it satisfies this differential equation as well, yeah, and it satisfies the initial value problem. But again, by a result that I have not proved, which requires this Bellman-Grunwald lemma that I said, I know that if one solution exists, then that must be the only solution because the solution is unique. Again, this is something I have not proved, I am asking you to take it on faith at the moment, but I have shown you at least that if you choose this as your initial condition, this particular thing as your initial condition, and this can be chosen as an initial condition, because after all these are all candidate solutions of the differential equation, that is x dot is equal to at into xt, right. So this can be a candidate thing, that could be a system trajectory that passes through this point, yeah, and once it passes through this point, that is equivalent to nothing but the origin. So if you are already at the origin, this differential equation will do zilch, nothing to it, it will continue to remain there because its position is at the origin, and because this x dot, this velocity is also 0, yeah, you can think of it in that physical sense if you like, the position is 0, the velocity is 0, therefore you will not budge an inch. And if you want to see whether acceleration is 0, jerk is 0, take higher and higher derivatives of this, it will only involve higher and higher derivatives of x on the other side, and each preceding derivative of x will be involved in the right hand side, which is already 0. So therefore this is identically going to be equal to 0, and therefore this is a solution, and by the Bellman-Grunwald lemma, which tells you that solution of a linear ODE is unique, if I can find one solution then I am done, I have already found one solution, therefore this is the only solution. So that means that for all t greater than t1, f of t1 times c is equal to 0, sorry, f of t times c1 is equal to 0. But what about all t less than t1, you might wonder, right. Also for all t less than t1, yeah, if I allow it to be sort of non-causal, that is also going to be equal to 0 because you are not going to propagate. After all, if you want to propagate in the reverse direction, then what you have to do is you have to just replace the sign of this at with minus at. So whichever direction you propagate this differential equation, whether forward or backward, yeah, if you are originally at the 0 position, the origin, your velocity is going to be 0 nonetheless. But this contradicts, right. So this tells you that if at one point that matrix ft ceases to be non-singular, then it's going to be singular for every t, right. So unlike in the general case of functions, like it could be singular for some particular values of t, but not singular for necessarily all values of t. But if those functions are these special functions that are also the solutions of this ODE, then they better be non-singular for every value of t, because the moment they fail to be non-singular for a particular value of t, you would be guaranteed to like conclude that they will be singular for every value of t. So therefore f of t must be non-singular for all values of t, alright. So here is our final claim for the day, and we will continue with this in the next lecture. So we have already shown that f of t must be non-singular for all values of t. If this condition is met, we call ft as the, so this is a definition, fundamental matrix, yeah. So what is this fundamental matrix? So to summarize, you have x dot of t is equal to at xt, yeah, and some initial condition given like this, yeah, alright. You want to solve this. So in order to solve this, if, so I already suppose this right at the beginning, that suppose someone already gives you a matrix ft whose columns f1 of t dot 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 till fn of t is such that ft is non-singular for all t and fit is a solution of, so let me call this equation star equation. So it is a solution of star for some initial condition, yeah, then Ft is called, this is the definition, no theorem or lemma statement, right, then this is called the fundamental matrix, okay, alright. So this is called the fundamental matrix, and it is easy to see that the fundamental matrix, so here is the claim, the fundamental matrix satisfies the matrix differential equation, that is what should I call it, m dot is equal to At mt, yeah, okay, this satisfies for some m t naught is equal to m0, okay. Why? Because obviously you take m0 to be equal to f1 t0 dot 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 till fn t0, and then you column wise, you differentiate entry wise this matrix, right. So you will see that immediately you take f1 dot, so you take f dot, yeah, is equal to f1 dot 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 till fn dot, and this is nothing but a f1 dot 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 a fn dot, yeah. So you can pull that out, so this is a times f1 dot till you have fn dot like this, so that is going to be nothing but a times f, yeah. So this is at of course, yeah, so at ft. So remember, this is not the same state equation, this is the matrix differential equation now. So this m is now an n cross n matrix, as is this m dot, okay. So this is what this fundamental matrix is all about. So in the next lecture we shall carry on this discussion a bit forward, and we shall see how this fundamental matrix is related to a very, very important matrix further on, which is called this state transition matrix, which will then allow us to establish the connection between this so called state transition matrix and the matrix exponential that we have been studying thus far for linear time invariant systems. In meanwhile, please brush up a bit on your understanding of linear algebra, particularly the notions of linear independence and otherwise, yeah. So we will meet next time and we will take this discussion a little further forward, so as to allow you to establish a connection between linear time invariant and linear time varying systems, but we will not dwell much longer on this, we will wrap this up well within the time limit of the next lecture, okay, and then we shall move into other important topics like stability. Thank you.